All right, here we are in section 2.1. The page number that you want to turn to is page 24 in your packet. Page 25. 2.1, increasing and decreasing piecewise functions. We're going to be looking at that today. Some new concepts that you're going to see in this video are the definitions of increasing, decreasing, constant. We're going to look at minimums and maximums, and really just analyze what a piecewise function is and how it looks like and the domains of those piecewise functions. Okay, so first, this is straight from your textbook. If you look at these graphs, if you are traveling up and to the right, the function is increasing. Right at the value -1, 5, right at that point, it is neither increasing nor decreasing. So notice that they put right here parentheses, so the interval that is increasing is everything up until -1, but not including. And then it changes to decreasing after that. Okay. Same for this one. It's decreasing down and to the right, and then up and to the right, and then it's increasing. Okay. And on this interval, the final graph, we have what is called constant. Nothing is changing. It's neither increasing nor decreasing. And you'll see the importance of that when you hit calculus. We talk about the change and how it's changing. So a lot of times we've done a little bit of change already with slope, like this is a positive slope. If it's increasing, it has a positive slope as well, just like this. But we don't know this slope, yeah? That slope is not a nice one, so meaning like it's not a straight line. So in calculus, you'll be seeing a little bit more of like how the slopes are actually changing. Now, there are formal definitions in your book, and you have an ebook on MyMATLAB. So if you want to take a look, it's in section 2.1. Okay. This is the formal definition for the increasing function. Okay. If it's increasing from A to B, where A is smaller than B, it implies that f of A is going to be smaller than f of B. Okay. So what does that look like? If you got a function here, you got A and B, and then you got f of A, and then you got f of B. You're going to have a function that's increasing. Is this point to this point, it's going to go up. Okay? F of B has to be bigger than f of A. If A and B, like A is smaller than B. If it's decreasing, that means what? What would I have to switch here is that f of A is going to be taller than f of B. So what did that look like here? That would be f of A and f of B. So that would be decreasing. Okay. So we'd have to change this a little right there if you want the definition for decreasing. All right, so let's look at this next example. The example is determine the intervals in which the function is increasing, decreasing, and constant. So let's write the word increasing, and then we're going to just determine the interval in which it's increasing. Okay? All right, so where is the interval increasing? Remember, it's up and to the right. So I'm going to just travel from left to right, and I'm going to make sure that it's going up. So this one's going down, and it looks like it's going up. It's increasing right here. That's it. Doesn't look like it's increasing anywhere else. So it's increasing on that interval. And how do we write that interval? You list the x value that it's going from to the next x value that it's going to. Not the y value, okay? Just the domain, the x values that it's increasing. So in this case, it'd be from 1 to 4. Okay? Now where is it decreasing? Now decreasing, I'm going to do in blue. It's going down to the right. So it's decreasing here. And it looks like it's decreasing. And there's an arrow, so that's going to continue on. So what interval is it decreasing from? Remember, you're going to list the x value that it starts at. So it's -1 to 1, and then from 4 to infinity. Okay. Reminder, you can pause and ask questions or kind of rewatch it to make sure that you're understanding. Okay. The last one is, where is it constant? It's only on that interval on the left side, and it looks like it goes to -infinity. It's going to keep going that way. and then it ends at 1. But there is a closed circle. But remember, we're not going to talk about endpoints on intervals that are increasing and decreasing. Okay, the endpoints don't count here. So it's constant from negative infinity to negative 1. All right, so graphically, those are the highlighted sections. The next thing we're going to look at are relative minimums and maximums. Now, a minimum and maximum is pretty obvious. It's like where the function is highest or lowest. But when you say the word relative, what does that mean? Well, sometimes there is no maximum. Like this right here, you see that arrow? It implies that it's going to keep going up. But in that area, you will have a relative maximum right here, okay? And in that area, I will have a relative minimum. Like this is implying it's continuing to go down, but I'll have a minimum right there. Now, the minimum and maximum are not your x values. It is the actual y values, okay? Like how high did it go? You're going to give me the y value. How low did it go? You're going to give me the y value. But you're going to say it occurs at this x value, okay? So the relative maximum will occur at x equaling negative 1, okay? Oh, negative 0.667, so not negative 1, negative 0.0667 occurs at x equals negative 0.667 and is 2.370. Like that's the maxima. And the minima occurs OCCURS at x equaling 2 and is that y value of 0. Maybe you could say y value of 2.370. Okay? So the next thing we're going to look at now is piecewise functions. So we have sometimes we have pieces that are put together on a graph using different formulas, different functions, different formulas, different pieces. So remember how I was talking, you can cut off like the function y equals 2x plus 3. You can cut it off and say only for this part. You can do that the same way for this. So looking at like example 3, here we have pieces that we can cut off, and we're going to write the equation for the functions below. And the way you write it is you say, like, for example, this is f of x, but it looks like I have 3 pieces here, but I actually only have 2, okay? So I'm going to write a curly bracket, and I'm going to write the two functions that I have here, okay? These ones are kind of easy because they're straight constant lines. And then you're going to define for what interval it works for, okay? So this one here is the function. It's a horizontal line, and it has an output of 2. So that's my first piece. And then it's only going to be for the interval from negative 1 to 2. So then you can say from negative 1 to 2. That is how you want to graph that part of my graph. Now I'm going to graph this one. Now this looks like two separate lines, but they're actually the same function. Notice it's a horizontal line again, and it's crossing at what y value? They all have the y value of negative 1. Okay. And what pieces am I going to graph it for? From this x value to that one, and this x value to that one. Okay. So if you want to list it instead of in this kind of interval notation, we could say using parentheses, so from negative 4, which I do want to put a bracket on because it's including, to negative 1, parentheses, and then from 2 to 5. Now how would I do it up above if I want to change that from negative 1 to 2? Okay. Those are the intervals on which you want to graph this function. Okay, that has 2 pieces, these 2 pieces, 2 and negative 1. Okay, so we're going to do it for this one now, this next one. Sorry. So I'm going to do f of x is equal to And I have 3 pieces here. I have a blue piece, a red piece, and a green piece. And notice that it all kind of is a continuous function. There's no breaks in it. So I'm going to go and do the blue piece. Actually, the red looks easy. So yeah, let's do that one first. Red. What's that piece? It's a constant, so it's a 1. And then what interval are we going to graph that from? We're going to graph it from -1 to 1. Let's not count it, the endpoints. We'll count the endpoints on the green and the blue, since the green and the blue are actually dots. All right, so let's go to the blue one. This blue one looks like a straight line. I can tell it has a slope of 1. And what's the y-intercept? If I were to graph it, it's going to cross at 2. So I'm going to write that equation of x plus 2. Okay, has a slope of 1, so 1x plus 2. But what interval am I going to look at it on? It goes from -infinity to the x value of -1. Let's include that one, -1. And the last one, it's actually kind of a harder piece. You notice that last one is a little curved. I have a point right here. If I were to graph more of it, can you guys tell me what this one looks like? It's a point right here. It actually is a parabola. It's going to look like this. Okay, so I have a parabola, and that's the nicest one. We call that one x squared. Okay, but only from what values? Now, what x values is going from 1 to this arrow on the right, which is infinity. So I'm going to say from, let's include 1 and go to infinity. If your brain is sore, that's good. You're learning, okay? So keep it up. It's a little bit hard with the piecewise. So I want you guys to try the next page and see what that looks like. Oops, it skipped up really far down. Go ahead and graph the line x and 2x plus 1. Press pause right now and try that. I'm going to graph the line x in green and then the 2x minus 1. I'll graph it in purple. Okay. So x is this line that looks like this, slope of 1. And I have the pleasure of being able to erase very easily. So I'm going to just graph this whole line. Looks kind of like that. Oh, well, imagine it was a straight line, okay? Now, as I go to the 2x plus 1 graph, before I do that, I'm going to cut off the piece. So I'm going to only look at it for x values that are smaller than 0. So I'm going to erase all of these values, and I cannot include 0. It's going to be an open circle on 0. And I'm going to draw this side. All right, so I just graphed the first one. Now I have 2x plus 1. Let's start that one on the y-intercept of 1. And then I'm going to rise and run by 2. Okay, now I can go down and to the right too, but I'm going to only include it for x values that are greater than or equal to 0. So I'm going to color that, that value in on 1, and then I'm going to just go to the right. So we just graphed what is called a piecewise function. So we have 2 pieces and we put them together on one graph. And it is a function. What do you guys remember about a function again? It has to pass that vertical line test. For every input, there's exactly 1 output. There's only one crazy spot, is like right there. What is my input? Is 0. Can you tell me what the output is? It's 1. Yeah, it's not 0. 0, 0 is, there's an open circle, so it's going to be 1. Very good. All right, so we have a data plan that's coming up, AT&T. This is something that happened to me when we went to California, Disneyland. Now we have like an unlimited plan that has a lot of data. But before that, you would have $50. You have to pay $50 for a certain amount of data. Let's say 25 gigabytes. And then if you went any gigabyte over, that 25 gigabytes, which happened to me when we went to Disneyland because we were doing a lot of what were we doing? Mapping Google Maps and using the Disney app to find lines that were less weight. And so I went over, but you have to pay for per gigabyte. So $5 every gigabyte over. I don't think it was that cheap. I gotta be honest. I think it was like 15. And then we were on a family plan, so my sister-in-law was using data too at that time. And then right before I was about to reset, I was trying to squeeze out all that data and really ration it off. She used some data and we had to pay another I think it was like $15 over per gigabyte. So it's okay. We live and learn. But that's kind of what this one is. C of 10. Let's go ahead and try to understand the real life situation. And keep in mind that this is going to be a piecewise function. Okay. So what would C of 10 represent? Okay, so 10 means how many gigabytes have we used? Remember, this 10 is going to be the number of gigabytes. That's my input. So the cost to use 10 gigabytes of data. Okay. How about C of 30? Oh, wait, let's compute it first. If I use 10 gigabytes of data, did I go over? No. C of 10 is going to equal $50. I have to pay $50 no matter what. I can use up to 25 gigabytes of data. Okay. But C of 30 is where I go over. So C of 30 would be the cost to use 30 gigabytes of data. So C of 30 is really that $50 plus the $5 over, right? Because it's per gigabyte over. Oh, how much over am I going? Looks like I'm going 5 gigabytes over. So I got to times it by 5. So this is going to be 50 plus 25. So instead of paying $50 that month, I went 5 gigabytes over, so I got to pay $75. So now we want to try to sketch it. It's a little bit challenging, so don't get too caught up in this one. But what's that going to look like? This is going to be my gigabytes, my X in this case, which is in gigabytes. And this is going to be my cost. Okay. So right away, I'm going to pay $50. Yeah. Let's mark that on our graph. And then how many gigabytes is my $50 going to go until 25 gigabytes? So this is a flat rate right until there. I still pay 50 at 25 gigabytes of data. Okay. But anything over is going to be $5 more per gigabyte. So next would be 55. So notice I got to hop up here. And then this would be 26 gigabytes. 27 gigabytes. Actually, this is called a step function, a step graph, or what do you call these? Integer step functions. Okay. Now, some of you might have graphed it this way, and that is okay too, because we don't really understand exactly what's happening. But right now, if I were to go any gigabyte over, I have to now pay $55. It's not going to be a linear function. It does grow linearly if you look at each integer rather than like whole number, rather than parts of a gigabyte. Okay. So then we write the formula for C of X. It's a little bit tricky. So if you guys can do it, go for it. It's going to say 50 from the values 0 to 25. And it can be 0, you can be 25. You don't have to use your phone at all. You can max it out at 25 gigabytes. But if you go over, you have to pay a certain amount of data. And you can use the integer function, which some of you might know, but we're just going to understand, write this as a linear function. How does it change? It looks like I have to add $5 for every gigabyte over. And how do we calculate the gigabyte over? In our case, I knew that this was 30, so it was 30 minus 25, yeah? So if I go, if my x is 30, I'm going to have to multiply by 5. If my x is 40, I'm going to have to multiply by 15. So it's really 50 plus the $5 per gigabyte over, which is going to be your x minus the 25. And that is for values that are greater than 25. So I'm going to have x is greater than 25. Okay? That one was kind of tricky, so if you had trouble with it, go ahead and watch the video again and try to understand what's going on. Now, if we could afford to spend no more than $70 on data in a given month, how much data could you use? Well, I think you guys can figure out. It's not a nice round number because we already just did one that costs $75, okay? So if we could spend no more than 70, I'm going to solve for x. I need to solve for x when c of x equals 70. So how do I do that? Well, I can take the piece above here and here, and then write 70 equals 50 plus 5 times x minus 20. Now you can do that algebraically. Now some of you might be able to see already that x has to be, instead of 5 gigabytes, it'd be 4 gigabytes, right? Because we're taking off five extra dollars. Now you can solve this algebraically by distributing, moving the 50, moving the 25, and then dividing by 5. Okay. So try to do that algebraically. Hopefully you can, and it will turn out to be a similar answer. All right. So now you have piecewise practice. You're going to practice these and work with each other in class, or if you're at home, try to get through these here. And I can go over that in a minute. Not a minute, but practice it with each other. Press pause, and then you can press play, and I'll go over this. You can continue watching. All right. So the function for this next equation. It's a piecewise. I have two graphs. I have one that's going from here to here and one going from here to here. So let's look at this piece here. It has a y-intercept of -2 and a slope. Looks like it's rising and running to here kind of nicely. So I'm going to count the rise. 4, 5, 6. 1, 2, 3, 4, 5. And the run. So 6 over 5x. And it's -2. And it's going from -infinity to 5. Now, I can include 5 there because you can include 5 in either piece. It doesn't matter. Okay? And the next line goes from here. It looks like this is the next nice point, and it goes to there. So it's going to rise 2, 2, 3, 4, 5, and run 5. So 2/5 x. Now, where is it going to intersect? If I go down to 1, 2, 3, 4, oh, it's going to intersect at 2, so +2. And what interval are we looking at this piece from? Looks like it's going from here to infinity. So what's that x value? From 5. And I'm not going to include it here because I included it on the one above. Okay. If you did it opposite, it's fine. It's also correct. Now, this piecewise does not have any breaks in the graph, so it looks like the domain is from -infinity to infinity. And the range also is from -infinity to infinity. Okay. Where is it increasing? It's actually increasing on all of the intervals except for this point right here. Okay? Right there, we call that a vertex. It's like a sharp point, and there's some kind of change or connection. We don't have it increasing or decreasing right at that point. The rest of it looks like it's increasing. So they go from -infinity to 5, and then from 5 to infinity. Like it's increasing everywhere. And then we say none. It's not decreasing anywhere. And then where it's constant, you would say, or maybe not none, you would say like NA, like not applicable for either of those. Okay, now where is f of 3? Now it says calculate, don't guess. We have to ask ourselves, which line am I looking at? Am I looking at this line or am I looking at that line? Which piece am I looking at? Where is 3? 1, 2, 3, right here. It's that value. How do I get that value? I plug it into the function where 3 exists, and that would be this top function, 6/5 times x minus 2. Okay, now it's not a nice value, so let's just make it as nice as we can. That's going to be 18/5 minus 2, and then to make 2 out of 5, it'd be 10/5. Are we okay with that? So 18 minus 10, I get 8/5. And if you wanna change it into a decimal value, what is that? 8 divided by 5, that's 1.6. Does that look like a 1.6 as a y value? Yeah, it does. 1.6. So we are good. We have checked our work. We feel confident in what we have gotten there. Okay, number 2. If you need to pause here and try number 2, pause it. Let's see. Oh, look, there's a dot right there at number 2. That's kind of cool. So I have actually 3 pieces here, okay? I have the one that's on the left and the right, and then I have a dot right there, just at that one point, okay? So let's go for the right side one. I think this one's kind of nice. It's a constant, so it's going to be this y value. That y value looks to be 3. And what interval is it going from? Looks like it's starting at 3, and it's going to infinity. Now it's not including 3. I have an open circle right there. What is the output right at 3? It's this one, right? That little dot. That output is 1 at x equals 3. Just that one value. And then the last one is this line. It looks like the slope is a 1, but it's going down and to the right. So my slope is a -1, and it has a y-intercept of 0. So that's kind of a nice one to graph. It's just -x, because the plus b is 0. And what interval are we looking at? Looks like it's going all the way to 3, but it's continuing to go up and to the right. Left. So it's -infinity to 3. But we don't want to include 3, this open circle over there. All right, let's now look at the domain. So the domain is traveling from left to right. Do I have any breaks in the graph? Yes, I do. I have one break right here. Does it exist at that x value? Yes, there is an output there. Okay, so I really don't have a break in my domain. It's -infinity to infinity because all the x values are represented. Then we ask ourselves, what's the range? What y values are represented? It looks like all of these y values are represented. Going up, I have that same y value, which is here as well. And then I have this y value, which is also here as well. Even though I have breaks, I have these y values. Okay? There is no y values below, though. So what y values exist for my range? It would start from this y value here and go all the way up. Okay? This is an open circle. So what is that, -3? -3 to infinity. All right. So some vocabulary. Where is it increasing? Is it going up and to the right anywhere on this graph? I don't see any of that going up and to the right. It's decreasing. Yeah, you see where it's decreasing from here down to here. So what interval is it decreasing on? -infinity to, remember, it's the x value that you want to give me. So not this x value, the y value, this x value. So from -infinity to 3. Don't include the endpoints on increasing or decreasing. Okay, and then where is it constant? Looks like it's constant on this interval. What is this x value to that x value? Starting from 3 to infinity. Okay, so let's now practice what's h of -10 and what's h of 46. So -10 is along this area. Yeah, -10 goes out that way. So I'm going to plug it into which function? I'm going to plug it into this piece, okay? And that's this one right here. So h of negative 10 is going to be negative 10, which is going to be a positive 10. Okay, so if you continue, we got negative 10 out here, you're going to get 10 as your y value. It's going to completely go up there. And what about h of 46? 46 is an x value that's all the way out this way. And notice that it's going to be plugged into that function. So h of 46 is just going to be 3. There's nothing crazy going on. It's always going to be 3 going out to the right. All right. So we just finished the notes on 2.1. What I want you to do now is to graph these following functions. So we have parent functions. This one is the absolute value of x. Use the table on the left to determine outputs for inputs. Pick nice ones. So I've started you on some nice ones with 0, 1, and negative 1. Plot it on the graph. Determine its domain and range, where it's increasing, decreasing, and constant. Okay, symmetry, and what stands out about the graph. Now it's going to feel repetitive, but I really want us to be very good with these parent functions. Okay, remember the goal in chapter 2 is really functions. In chapter 1 and chapter 2 is understanding what a function is. These are the most popular functions that you'll be seeing, and we're going to be seeing it in our next exam on graphing with parent functions. Okay, so go ahead and work on this. Parent functions, we got absolute value, we got x squared, we got the square root of x cubed, the cubed root of x. So this one, you might want to think about what nice values can be cube rooted. 2 to the x. Now remember, x here is an exponent, so this is going to be an exponential graph. And this one didn't get printed out, so write it in. It's log base 2 to the x. So that's on page 35, log base 2 to the x. Remember, that kind of undoes a base 2, so if you can think of values that work, I would not use these two values. I would use 2 and 8 would be the next one. That's my hint to you on that one. 1 over x. You might have some fractions going on. Same for that one. Think about when you square it though and how that affects your graph. So I want these all completed before I see you next time, up to page 37. And yeah, make sure you fill that out. Come with questions if you have any, or ask Mr. Kakutani if you're in my early college math 103. And I will see you guys when I come back. If you're in my early college math 103, view 2.2 on the next video.